Thank you. Okay, so now let's move on for some first presentation by the head of the science department of ESA, McCaughrean.
Thank you very much. Good morning, everybody, and welcome to ESTEC for this 47th ESLAB Symposium. It's my privilege to speak to you this morning because I'm the head of the Research and Scientific Support Department, which is actually the successor of what is ESLAB. So I thought I would spend a couple of minutes this morning telling you what ESLAB was and is today, just to give you a bit of the history. Why do we have these ESLAB Symposia? So ESLAB as symposia stretch back to 1967 in an unbroken chain, and that stems back to the days before the European Space Agency. It goes back to when there was ESRO, the European Space Research Organization, and ELDO, the European Launcher Development Organization. And that was in the early 1960s. These two then joined in 1975 to form ESA, the European Space Agency that we have today. So at the beginning, ESLAB was a key part of ESRO. ESLAB, European Space Laboratory, as you might pick out of that, was effectively the scientific heart of ESRO. It's where the scientists were going to come together and learn to exploit space-based data, scientific data, because there was really no long-term heritage in this in Europe or anywhere else really at that point. Now, we're in ESTEC today, rather large establishment as you know, but ESLAB started off in a much smaller place. It started off in a hotel in Noordwijk, the Hotel Zinger. First off the Hotel Helmhorst, then it moved here into some prefab buildings as ESTEC was being built up. Those prefabs then burnt down, which is a bit unfortunate. So we had to move back to a hotel, the Hotel Zinger in Noordwijk, and then to another building in Noordwijkerhout. And I'll show you that just for the historical benefit. Now, of course, if we had actually stayed in a hotel in Noordwijk, you would have had a lot less far to come this morning, and I apologize for getting you up early on a day like this, but probably wouldn't have fit into one of the hotels as we have such a big room here this morning. So, ESLAB then became known as the Space Science Department in 1967, moved here in 1968 to join with the engineers. Later on, it was renamed RSSD, the Research and Scientific Support Department, which is a key part of the Directorate for Science and Robotic Exploration. And a key part in the sense that it is the home of the project scientists for all of the space science missions which we are developing and which we're operating today. And the project scientists, the one that you know best, of course, is Jan sitting in the front here, are cradle to grave. They get these projects right at the various early phases when they're studies, and very often they go on to pick them up when they are put into implementation, construction, and then through operation, and even into the archival phase. And that we are therefore responsible for making sure that the scientific requirements, which you, the science community, set, are put into implementation, that the satellites are capable of actually executing these scientific requirements, and that they then deliver upon it. So Jan finds himself in the very fortunate position, after many years of hopefully semi-forgotten toil, I doubt it actually, I doubt he's forgotten any of it, where he's now in the phase of reaping the rewards of the mission that he's been working on for many years, along with many of you in the room, of course. Planck, of course, fits into a rather broader set of missions that we're currently operating and developing. I'm not going to go through them in detail. These are our solar system missions, many of which are currently in operation, and several, as you'll see, including Solar Orbiter and JUICE, which are being built for launch in the Cosmic Vision program. The first launch will be Solar Orbiter in 2017, and we're also, JUICE will be in 2022. Going out to Jupiter. We also have a whole series of missions, of course, operating, looking at the universe beyond the solar system, doing astrophysics and cosmology, and Planck is there on your left-hand side at the far infrared microwave end. And Alvaro already mentioned this morning that Euclid, which is the M2 mission from Cosmic Vision, should fly around 2020, and we'll explore the dark universe, in particular dark energy and dark matter. So I'll come back to that in a couple of minutes. Now, I'm not a cosmologist. Many of you know that. I'm afraid I've concerned myself with rather more prosaic things over the years, such as the formation of stars and planets. I suppose they come out of cosmology in the end. But since moving to ESA in 2009, of course, I've had to concern myself with all of the missions that we're operating. And Planck has been, in many ways, preeminent amongst those, along with Herschel, because they were launched just before I arrived and have been producing the bulk of their new science data over the last few years. Now, that led me into the rather interesting situation a couple of weeks ago. Many of you were there, many of you will have watched it live, the press conference that we held in Paris, where I was put on the spot and had to then, in an interview with television, immediately afterwards, I was thrust into the limelight and asked to explain why it was that the anomalies in the CMB told us something about inflation and possible multiverses. This was awkward enough to begin with, let alone the fact I had to do it in German. So this is Planck's CMB image, which you're all very familiar with. It's a bit washed out, I'm afraid, in the light in the room here. And rather than talk about the anomalies, which of course there'll be a lot of discussion here, I'm sure, in this conference, I wanted to pick on something else as sort of the little theme for my 10 minutes here this morning. And that's the extraordinary fit of the CMB and the power spectrum, which you see here in the top left. The extraordinary fit to those 7 peaks, 7 acoustic peaks, to the model of lambda cold dark matter, lambda CDM. And in doing so, of course, that's slightly revised the contents of the universe, changed the proportions of dark matter and dark energy, and changed the amount of ordinary matter slightly relative to previous results, most notably WMAP and the missions that went before it, and also the ground-based data. Now, in picking on this, I was struck during the press conference, and in fact, looking at Twitter during the press conference, and those who were in the room at the time will remember me talking about this, there was this rather odd reaction that many people turned around and said, well, that's a bit dull, isn't it? You know, I mean, it fits perfectly. There's nothing new here. Planck has discovered the MBU, the maximally boring universe. Now, it strikes me that that's a little bit, unfair, to say the least. And it also strikes me that it comes from the same sort of place that people have been talking about the LHC, the Large Hadron Collider, and the Higgs, and sort of complaining that all we found is a vanilla Higgs boson. I mean, I do struggle with that a little bit, because, sure, it's always nice to discover new things. We'd hope that every rock that you lift up and look underneath, that you'll find some new species, something interesting. But life isn't like that. Sometimes it's just as exciting to confirm a model in extraordinary precision, like the lambda CDM model here has been reproduced with the data from Planck. And I think, it's occasionally we have to stand back and take a bit of perspective on this, because it's not that many million years since we came down out of the trees, and for us to be able to generate models which we can then make predictions with, and then go and observe with these astonishing pieces of machinery and fit in such detail, I think that really says something quite astonishing about humankind as a species. Now, you know much better than I do, of course, that the fit to the Planck power spectrum can be fit just by the standard 6 parameters of lambda CDM. There was no need to invoke any further parameters. And as I was thinking about that during the press conference and afterwards, of course, 6 parameters reminded me of a famous quote from a book by Lewis Carroll. Many of you may have read it to your children or read it yourself when you were younger, called Through the Looking Glass. And there's a quote in there where the White Queen says, "I have on occasion believed 6 impossible things before breakfast." Now, that's not to say that all of the parameters which go into lambda CDM are impossible per se. Maybe they're all possible, but you have to admit that at least a couple of them, dark energy and dark matter, and maybe inflation, it's not one of the parameters, but it's part of the model, they do stretch the imagination quite considerably. So, in thinking about that quote and thinking about believing impossible things, which I think actually is pretty much the state of modern physics, that much of what we appreciate in modern physics is very hard to associate with our common sense monkey view of the world, if you like, I thought I'd go and look at the whole quote. What was the White Queen actually talking about at that point? So I'll try not to do the accent, as I'll end up sounding like Elizabeth II, but let me just read this out to you because I think it is remarkable. So at this point, the White Queen is trying to distract Alice from crying at this moment. So the White Queen says, well, let me ask you a question. How old are you? And Alice replies, I'm 7.5, exactly. And the White Queen, you needn't say exactually, the Queen remarked. I can believe it without that. Now I'll give you something to believe. I'm just 101, 5 months and a day. I can't believe that, said Alice. Can't you? The Queen said in a pitying tone. Try again. Draw a long breath and shut your eyes. Alice laughed. There's no use trying, she said. One can't believe impossible things. I dare say you haven't had much practice, said the Queen. When I was your age, I always did it for half an hour a day. Why, sometimes I've believed as many as 6 impossible things before breakfast. So again, the state of modern physics, perhaps, to some extent. So in emphasizing that quote there, I also want to emphasize this quote, which I thought was quite an interesting one, the one at the top here, about the Queen being 101, 5 days and 5 months and a day. So when I pulled this quote up yesterday, I started thinking, well, what was happening roughly 100 years ago? Of course, physics was in turmoil roughly 100 years ago. This was the time, the genesis of quantum mechanics and the beginning of relativity as well. The two key elements, if you like, that Planck is all about. Not only Planck, Max Planck the man, but the idea that the universe started off as an object at 10 to the minus 35 meters, inflated by a factor of greater than 10 to the 78 in volume, on a time scale of 10 to the minus 34 seconds. I mean, these things speak about quantum mechanics. And of course, the universe beyond that in lambda CDM is driven by general relativity. So then I thought, well, I wonder what was happening exactly 101 years, 5 months, and 1 day ago. And very fortunately for this talk, otherwise this would fall flat on its face, this conference was taking place, the famous first Solvay conference in Brussels in 1911. On November the 1st, 1911, 101 years ago, 5 months and 1 day, was the middle of this particular conference. And those of you will know that this conference was had to do with radiation and the quanta, was stimulated by the work of Max Planck, who's here. Involved the youngest person in the room was Albert Einstein at this point, and many other luminaries of modern physics. I won't read the names out, you can see them there, but including Jeans, Rutherford, Langevin, Lawrence, and of course this meeting was chaired by Hendrik Lawrence, who was a professor just down the road here in Leiden, and he chaired all the Solvay conferences. Interestingly, I've seen this picture many times, as I'm sure you all have, but I looked at it yesterday carefully, and I realized that Solvay here had actually been photoshopped in. Actually, he was just stuck in afterwards. They sat somebody, he wasn't available for the photo. He was the person who set the conference up. So they sat somebody there, and the photographer glued a picture of Solvay on afterwards. And which, of course, is a little bit like the center part of the galaxy in the CMB image, right? Okay? Because that's not real either. We didn't tell everybody that, I know. But so this conference, of course, was at the start of a stunning series of meetings, and it culminated in 1927 with the 5th Solvay conference, where really quantum mechanics was sealed. And in the interim between 1911 and 1927, an important discovery or an important observational verification was made of a challenge that Einstein made in 1911 when he was working in Prague. Namely, that general relativity, his burgeoning theory, predicted that starlight coming past the limb of the sun during a total solar eclipse should be deflected, or it should in any case, but should be observable in a total solar eclipse. And of course that was proven, that was tried earlier in the decade and then proven in 1919 by Eddington, who measured this, took this photograph here, and here are some of the stars outlined. And Eddington then went on to become one of the great proponents of a cosmological view of the universe that involved relativity. And in fact, he also was involved in promoting the use of the cosmological constant, if you like, the lambda at the front of lambda CDM. Because in the 1920s, Slipher and then Hubble, of course, discovered the expanding universe. Einstein didn't know about it when he first introduced the cosmological constant. So this again was a burgeoning time in the 1910, 1920s epoch. But I found one more very interesting thing out last night in my research, namely that Eddington came up with a very interesting piece of mathematics, which I'm sure many people in the room don't know, because I didn't, and that Eddington developed a thing called the E number. Okay? Now, the E number, Eddington was a very, very keen cyclist. The E number is the number of days on which you have cycled more than E miles. Okay? And Eddington's E number was 87, which is quite an impressive number. Mine is 25 since I moved to the Netherlands, which I think is pretty pathetic. But so I obviously need to get out on the bike more often. But I have a few more years to catch up with Eddington. Now, you know, the E number does have a modern sort of reincarnation, of course. But of course, you know, I thought I'd put this in for bicycle friends. You know, Einstein probably didn't have this is the only picture of Einstein on a bicycle, so I don't think he had a very big E number. But of course, yes, as people have pointed out, this is actually very related to what we know as the H index today. Okay, and so in summary, this conference, I suspect, will be boosting many people's H index in the next few months. Many of you were, of course, co-authors on the great swathe of papers that were published, or put into AstroPH at least, a couple of weeks ago. And I'm sure many of the scientific results that will be discussed here will end up driving the H index of the scientists in the room, of the mission. And as much as that's a measure of anything, I think it's a measure of how important Planck will prove to be in 21st century physics. And not only, of course, in this conference related to the CMB, but also related to all of the foregrounds, as you see in Planck's maps from 30 to 857 gigahertz. With such precision and such resolution, I think that Planck has already made an enormous impact on cosmology and also long wavelength galactic science and all of the things between here and redshift 1100. Because this is only the beginning as well. So far, you're only working on 15.5 months of data. There's much more in the archives. And I know that you'll all be working extremely hard over the next year and a bit, shall we say, until the next data set is released. And then let's see what happens then. Let's see what the polarization data bring. With that, I'll finish. Welcome to ESTEC, welcome to ESLAB, and enjoy your conference. Thank you.
Thank you, Mark. Thank you. So let's